Here's my second video on curve sketching. In the first one we did curve sketching for polynomial functions. This one I'm going to go over an example doing curve sketching for rational functions. So it's going to be the same process. We're going to use the same algorithm for curve sketching. We're going to look at intervals of increase and decrease using the first derivative, look at intervals of concavity using the second derivative, and use all that information to help sketch the curve of the function. So here we go. Let me just go past the first one we did, right? In the first video, we looked at the curve sketch of this polynomial function. So we've already done that. Let's do this example here where it's a rational function, right? We have a function in the denominator. There's a variable in the denominator. And it may help if I write the denominator in standard form. So let me just expand the denominator quickly. It would be x squared minus 3x minus 4 if I expanded that out and collected. So for this rational function, I want to know, what does the sketch of this graph look like? So we're going to go through the same algorithm. This one is going to be significantly different than the last one, mainly because rational functions can have asymptotes. So we're going to find vertical asymptotes by looking at what x values make the function undefined. And what would make a function undefined is whatever would make the denominator equal 0. So in this case, what would make this denominator equal 0 if x was either -1 or 4. So you'll find vertical asymptotes at -1 and 4. This function also has a horizontal asymptote, and in fact, any function that has a function in the denominator which is higher degree than the function in the numerator, right? The denominator is degree 2 and the numerator is degree 1. So any function where degree of denominator is greater than degree of numerator, it has a horizontal asymptote at y equals 0. Reason being because if I were to plug in an infinitely big x value into this function, the denominator gets infinitely bigger than the numerator, meaning the y values are going to be approaching 0, right? 1 over an infinitely big number is going to be approaching 0. And same if I were to plug in negative infinity, right? Same idea. So let's just plot those quickly on our graph. So we have vertical asymptote at -1 and 4. So let me just add those in quickly. So at x equals -1 and x equals 4, I have vertical asymptotes, and there's a horizontal asymptote at y equals 0. Okay, so that's step 1 of our curve sketching algorithm, where we state any asymptotes or holes in the graph. Right? If there was an x value that made the numerator and the denominator be 0, there would be a hole in the graph at that x value. Step 2, what we're going to do now is we're going to find the x-intercepts and the x and y-intercepts of this function. So an x-intercept is any x value that has a y-coordinate of 0. So if I were to set this to 0 and solve, you would see quickly that it's not possible. Right? How can a fraction be equal to 0? Well, only if the numerator was 0. So how can 0 equal 1? Well, that's not possible. There are no x-intercepts. And that should also make sense to you because we said there is a horizontal asymptote at y equals 0, meaning the function cannot have a y-coordinate of 0, meaning it doesn't have any x-intercepts. Y-intercepts, we could calculate that by setting x to 0 and solving. So we've got 1 over 0 plus 1 times 0 minus 4. So that would be 1 times -4. That's -4. So we've got 1 over -4, which is -0.25. So let's go ahead and plot that on our graph. So we know a y-intercept at 0, -0.25. So there's our y-intercept. Next step in our curve sketching process is to determine the critical points. And remember, what are critical points? Critical points are points that make the derivative either equal to 0 or undefined. Or I could call them restrictions of the first derivative. So we're going to find any x values that are either a 0 or a restriction of the first derivative. That's what a critical point is. The critical point is the x and y value, right? We actually need the y coordinate that goes with them, but you get my point. A critical number is a number that makes the first derivative 0 or undefined. So let's go ahead and first find the first derivative. So we're going to need the derivative of this function. That's why I wrote it in standard form. I think it's going to be a little bit easier when it's in standard form to do the derivative. So f of x equals 1 over x squared minus 3x minus 4. So we could do the derivative of this in a couple different ways. I'm going to do quotient rule, but if you wanted to, since this is a reciprocal function, we could rewrite this as x squared minus 3x minus 4 to the power of -1, and then use chain rule. But I'm just going to do quotient rule. So f prime of x equals derivative of numerator, which is 0, times denominator, so x squared minus 3x minus 4, minus derivative of denominator, so 2x minus 3, times the numerator. And this all needs to be over the denominator squared. So all over x squared minus 3x minus 4 squared. And then I'll just simplify the numerator by collecting any of my like terms, right? 0 times that factor, so that's gone. Minus 2x plus 3. So I've got negative 2x plus 3 over my denominator squared. There we go. So that's my derivative. Okay, so any critical number would be a number or an x value that would make this equal to 0 or undefined. So what would make this equal to 0 is whatever would make the numerator 0. So 0 equals negative 2x plus 3. 2x equals 3, divide the 2. 3 over 2 is 1.5. So that's the critical number. And then what we need to do is find the critical point by plugging that x value actually into the original function. And I believe we get negative 0.16. So the critical point has the y value associated with it. So our critical point is actually 1.5, negative 0.16. At that point, what do I know? I know there's a horizontal tangent because I know the value of the first derivative is 0, which tells me there would be a horizontal tangent at this point. That point may be a local max, it may be a local min, it may be neither. It may be a point like this in an S shape that has a horizontal tangent but is not a max or a min. So I don't know which of these it is, but when we do our sign chart and test for, we test for changes in increasing and decreasing intervals of concavity and stuff, we'll be able to determine that. But I know that's a point that is going to be a key characteristic of my function. Now, other critical numbers are numbers that make the denominator be 0, right? Because that would be a restriction on the derivative, which means there would be a vertical asymptote there. Now, keep in mind, when we find the restrictions, the critical number is a 0 of the numerator or the denominator, but only if that number is also in the domain of the original function. And I'll show you what I mean by that in a second. So if we find the restrictions of this function, that would be what makes the denominator be 0. And here's our denominator. And remember, this came from factored form x minus 4, x plus 1. All of that being squared would be the same as putting a squared on both of those. So how could this be 0 if x was 4 or if x was negative 1? So the derivative is undefined for those two x values. So they are critical numbers if those numbers are in the domain of the original function. But if we look at the original function, notice the original function doesn't exist at 4 or negative 1. Therefore, they can't be critical points, right? These cannot be critical numbers because the function doesn't even exist at those numbers. So we don't have to worry about those. Those are asymptotes on our function. So the restrictions on the first derivative are actually not critical numbers in this scenario because those numbers are not in the domain of the original function. If they were in the domain of the original function, that would mean that at those numbers, there would be a vertical tangent, meaning maybe it was a cusp or something in our function at that point. But we don't have to consider them for this one because they're not in the domain of the original function. Okay, the next thing we want to do, I could plot this point, I suppose, 1.5, negative 0.16. 1.5, negative 0.16, it's like right here. Okay, so we've got a couple points on our function now. Okay, now let's find the possible points of inflection. Remember, a point of inflection is where the function changes from concave up to concave down. So in order to figure that out, we're going to look at when is the second derivative either equal to 0 or when is it undefined. So we're going to find the zeros and the restrictions of the second derivative. And so these possible points of inflection, they're only possible points of inflection if they make the second derivative 0 or undefined and are also in the domain of the original function. So let's start by finding the equation of the second derivative. So let me rewrite the first derivative. It was just right here. It was negative 2x plus 3 over x squared minus 3x minus 4 squared. So in order to differentiate, so to get the second derivative, I need to find the derivative of the first derivative. And I'm going to do quotient rule, and within the quotient rule, there's going to be a chain rule. And if that intimidates you, make sure you go back and watch the videos reviewing those rules. So quotient rule, derivative of numerator, which is negative 2, times the denominator, minus the derivative of the denominator, which I need chain rule for, derivative of outside function with respect to the inside function, times derivative of the inside function, times the numerator, all over the denominator squared, right? That's what quotient rule tells me to do. So x squared minus 3x minus 4 squared, squared. That means to the 4. Okay, so we're interested in when is this equal to 0 or undefined. It'll be useful if we simplify this before we do that. And I want you to notice that the first term and the second term both have a factor of x squared minus 3x minus 4. I mean, this one has 2 of them, that one has 1 of them. But I point that out because we can common factor one of those out and cancel it with one of the factors that are in the denominator. So I'm going to go ahead and do that. So I'm going to take out an x squared minus 3x minus 4. And what I'm left with from the first term is just a negative 2 times x squared minus 3x minus 4. Right, one of those x squared minus 3x minus 4s are gone. And then the second term, I'm left with the negative 2, the 2x minus 3, and the negative 2x plus 3. And this is all over x squared minus 3x minus 4 to the 4. So I did this because that will cancel with one of those. So we're left with 3 of them in the denominator. Okay, the numerator, I'm going to expand and collect any like terms I have in the numerator. So I'm just going to, I'm going to do all my distributing and collecting. So I've got negative 2x squared plus 6x plus 8 minus 2 times my product of those two factors, so negative 4x squared plus 6x plus another 6x, that's plus 12x, minus 9. And it's all over my denominator still. And let's just do one more step of collecting here. So I've got a negative 2x squared, and then here I'm going to have a plus 8x squared, so that's 6x squared. I've got a 6x, and then I'm going to have a minus 24x. So that's going to be negative 18x. And I've got a plus 8, plus 18, that's going to be plus 26. And this is all over the denominator still. Okay, a possible point of inflection is a point that is either going to make this be 0 or undefined. So how could this be 0? Well, if the numerator was 0, it would make it 0. Okay, so what I have here is a quadratic. If I want to know if a quadratic could be equal to 0, I could just check the discriminant. So let's check b squared minus 4ac. If we check b squared minus 4ac, I mean negative 18 squared minus 4 times 6 times 26. And if we do that, we get negative 300. So the fact that b squared minus 4ac is less than 0, it means there's no way that this quadratic could be equal to 0 because the discriminant is negative. So therefore, there's no way this function could be equal to 0, which means I get no possible points of inflection from the zeros of the second derivative. What about maybe there's a way that it could be undefined? So that would mean making the denominator equal to 0. So remember, this came from the factors x minus 4, x plus 1. And this would all be cubed, so cubed, cubed. So this could be 0 if x was 4 or negative 1. But remember, neither of those x values are in the domain of the original function, not in domain of f at x. Therefore, they can't be points of inflection because the function doesn't even exist there. So no points of inflection. Now the function may have changes in concavity, but it would be at vertical asymptotes. It wouldn't be at an exact point on the function. So we have no possible points of inflection because there's no way the second derivative can be 0, And there are no x values that are in the domain of the original function that would make this be undefined. There are x values that make this undefined, right, 4, -1, but they're not in the domain of the original function. So we have no possible points of inflection. Okay, so now let's actually try and go ahead and find our intervals of increase, decrease, and our intervals of concavity to accurately sketch the graph. So when you make your sign chart, make sure in your sign chart, on the very left you have -infinity, on the very right you have infinity, and then in between, you're going to have all of your critical numbers, all of your possible points of inflection, and all of your vertical asymptotes, making sure to put them in ascending order. So we're going to include in our table vertical asymptote, and critical number. And if we had a possible point of inflection, we would include that too, but we don't have any. So we're going to include 1.5, -1, and 4 in our table, making sure that they're in ascending order. So -1, 1.5, 4. So just to summarize, these numbers, you're going to use any vertical asymptotes, any critical numbers, or any possible points of inflection. So you're going to consult all three of those things and put those numbers up here. Those are going to be our dividing points for the intervals of the function. Now within each interval, we're going to pick a test point. So I'll just do that quickly. I'm picking a test point within each interval, right? Between -1 and 1.5, 0 is in that interval, so I'll choose 0. But you could choose anything within it, in that interval, and so on. Now we're going to test those x values in the first derivative, in the second derivative, and then comment on what that tells us about the original function. So if I were to test -2 into my first derivative, if I plug -2 into the first derivative, well, I know the denominator is always going to be positive, right, because it's squared. But if I plug -2 into here, -2 times -2 is 4, plus 3 is 7, so it's positive. So I'll put positive over a positive, it's going to be positive, right? I only care about the sign of the first derivative and the second derivative in each interval. How about the second derivative? If I plug -2 into the second derivative, I'll let you trust me on this one, or go ahead and plug it in and test it. But if we plugged -2 in for all these x's and evaluated, we'll get a positive answer as well. So what does that tell us about the original function? Well, the first derivative tells us that the original function is increasing over that interval. And the second derivative being positive tells us that the function is concave up over that interval, right? Because the tangent slopes are positive and the tangent slopes are increasing, meaning we have an increasing function that is concave up. So it's going to look something like this over that interval. How about the next interval? If I plug 0 in for the x's, so if I plug 0 into here, I'll get 3 over a positive number, so that's positive. If I plug 0 into here, I'm going to get a positive over a negative, so that's negative. So this being positive tells me that the original function is increasing. But the second derivative being negative tells me that the tangent slopes themselves, although they're positive, they are decreasing, which means the function is concave down. Concave down. So I need to draw an increasing function that is concave down. So it's going to look like that. The next interval, if I plug 2, I'm going to get a negative over a positive. That's negative. If I plug 2 into the second derivative, I'm also going to get a negative answer. So that tells me that the original function is decreasing. Right? The first derivative is negative, telling me the tangent slopes are all negative. So the function's decreasing, and those negative tangent slopes are decreasing, which means that the function is concave down. So negative tangent slopes that are decreasing. So the function is decreasing and concave down. So it's going to look like this. And my final interval, if I plug 5 in, I'll get a negative over a positive, which is negative. If I plug 5 into the second derivative, I will get positive. So the original function, since the first derivative is negative, I know the original function is decreasing. And because the second derivative is positive, I know it's concave up. So I need to draw a decreasing function that is concave up. So it would look like this. Right? Another way to think about this, the tangent slopes are negative. Right? First derivative tells us about the tangent slopes. The second derivative tells us how those tangent slopes are changing. So I have negative tangent slopes that are increasing. Right? The tangent slopes would all be negative, but they would be increasing. So if you look here, we really have a pretty decent sketch of our function, right? Remember, there's a horizontal asymptote, vertical asymptote, vertical asymptote. But as long as we follow what the first and second derivatives tell us, then we have a good picture of what our graph's going to look like. We just have to transfer this onto our graph. So hopefully you made the connection here. When I was commenting on whether the function was increasing or decreasing, I was looking at the sign of the first derivative. When I was commenting on whether it was concave up or concave down, I was looking at the sign of the second derivative. So did we have any local max or min points? Were there any points where the function changed from increasing to decreasing or vice versa? Yes, it changed from increasing before 1.5 to decreasing after 1.5. So at 1.5, notice there's a local max point. So we've got a local max at 1.5, and I believe it was negative 0.16, and we've already plotted that one. And there are no points of inflection, although there are changes in concavity at -1 and 4. There are changes in concavity. I can't call those points of inflection because they're not actually points on the graph. Remember, this is a vertical asymptote, this is a vertical asymptote, so the functions don't actually exist there. So there are changes in concavity around the vertical asymptotes, but we can't call those points of inflection. So let's go ahead and sketch what this looks like. So in the interval x less than -1, I need to draw an increasing function that is concave up, so it needs to look like this. So increasing function concave up, well, it can't look like this because that's going to go through the asymptote. Now I know some functions can go through horizontal asymptotes, but this one doesn't. It's going to look like, I mean, that's not perfectly accurate. We could calculate some more points if we wanted to, but that's the general shape of this curve, increasing and concave up in that interval. Between -1 and 1.5, it needs to be increasing and concave down. So in this interval, it was increasing and concave down, so it looked like this. And then if we looked at the next interval from 1.5 to 4, it was decreasing and concave down, so it looked like this. And then in the final interval, from 4 to infinity, it was a decreasing function that was concave up. So it looked like this. So there's our final curve sketch of the function. So here's the Desmos representation of the function. Let's just take a look at, I want to take a look at the signs of the first derivative and second derivative, make sure you understand how they connect to the slope of the tangent. So the first derivative sign tells you, like the first derivative literally tells you the slope of the tangent, right? So if we look in this first interval, x less than -1, the tangent slopes, the first derivative, are all positive. Now what's happening to those tangent slopes? Well, right there it's 0.3, here it's 0.4, here it's 0.5, right? Those tangent slopes are increasing, which is why the second derivative is positive. They tell you the tangent slopes are increasing. They tell you how the first derivative is changing, which results in the function being concave up. If we look in the next interval, the tangent slopes are all positive still, right? So between -1 and 1.5, the tangent slopes are all positive, but those positive tangent slopes, if we look at these values here, those positive tangent slopes are decreasing. Right, and the actual value of the second derivative tells you at what rate they're decreasing, but the fact that they're decreasing is what makes this second derivative be negative. Positive tangent slopes where the tangent slopes are decreasing. So that results in a function that the function itself is increasing, but is concave down. In the next interval, from 1.5 to 4, notice all the tangent slopes are negative. That's why the first derivative is negative, right, because they tell you the tangent slope. And those negative tangent slopes are decreasing, which is why the second derivative is negative. So we have a decreasing function that is concave down, right? The original function is decreasing, and it's concave down. And then if we look in the last interval, the tangent slopes are negative, and what's happening to those tangent slopes? They're increasing, right? Here the tangent slope is -3.5. Here the tangent slope is -1.8. Here the tangent slope is -0.9. Right, those values are getting bigger. The tangent slopes are increasing. That's why the second derivative is positive in that interval. And the second derivative being positive tells us the original function is concave up. The first derivative being negative tells us the function is decreasing. Okay, hopefully that video helped you out. The next video I'll be looking at is optimization. So using derivatives to solve optimization problems. So make sure you subscribe, make sure you like the video, and stay tuned for what's coming up next.